Now, the reason that we have calculus is because we got to studying rates of changes, which is something that should sound familiar. What's another word for rate of change? Like from Algebra 1? The slope. Now, we only found slopes of lines in Algebra 1 for linear equations because they were the only ones that have like direct slopes since they're a straight line or a diagonal line. However, we started to need to find the rates of changes of graphs and of functions that were not straight lines. And so mathematicians that were inventing calculus way back when started to work with ways to do this. That was the problem they were trying to solve. So the thing that they started with was finding average rates of change. Now, this is going to make sense in a linear concept. It's not going to make sense at first for like this cubic function I have written here. The average rate of change is the total distance traveled divided by the elapsed time, which makes sense because distance divided by time is speed or velocity or slope. But when we are finding the rates of changes for graphs that are not linear, we're going to be looking at the slope of the secant line. Now, secant is not like the trig version of secant. We're talking about the geometry version of secant, which is where you had like a circle and there was a line that went through the circle. That's called a secant line. So it touches the shape in two places. So if we apply that definition of secant to like this point and this point on this graph, I technically can find the average rate of change between those 2 points. I'm just looking for the slope of the line that goes between them. And that's fine and dandy, but especially for like this example, that's a cubic function and I'm only looking at this point and this point. I'm basically ignoring the fact that this cubic function goes all the way back down and all the way back up because I'm only looking at these 2 points to find the average change between them, which is fine. That's what average rate of change is. It just ignores the fact that the graph does other stuff in between those 2 points. So the formula for this, because it's essentially a slope, it's going to look very much like the slope formula you've used since forever. AROC stands for average rate of change. That's me being lazy. Are y'all okay with that? Average rate of change. It's the same thing as a velocity or an average velocity. So that's the physics way of talking about it. V average is for average velocity. And the mathematics for it is that it is the absolute value of the change in distance divided by the change in time. A little triangle right like that is called a delta. Delta means change. So really, what that means for us is that we have a formula, distance 2 minus distance 1, absolute value, divided by time 2 minus time 1 will give me the average rate of change. Now again, that should look familiar to you. What does that formula kind of look like from Algebra 1? Yeah, it sort of looks like the old slope formula where we did y2 minus y1 over x2 minus x1. And it 1000% is the same formula. But because we're talking about average rates of change, we don't really care about positive or negative, which is where the absolute value comes in. And we are no longer going to be using x's and y's for calculus. A lot of calculus is done with distance versus time or position and time. So most of the time your variable in calculus is going to be a t for time because it's a real life thing. So mathematicians were pretty happy with that. We said, okay, cool. We can find the average rate of change between 2 different points on a graph. Amazing. And then somebody's like, yeah, but what about exactly at 3? What is the exact speed or the exact rate of change of this object at time 3? And mathematicians were like, how do you find an instantaneous rate of change? So instantaneous rate of change, IROC is what I'm going to shorten it to later, is speed at a specific instant in time. So not an average of 2 times, but at a very specific time. Graphically, what that means is that it is the slope of the tangent line. And again, tangent not in the sense of trig tangent, but in the sense of like a geometry tangent. So in a circle, a tangent line was a line that just came through and touched the circle once. That's a tangent line. The trouble with tangent lines is I could draw it like that, or I could draw it tilted a different direction because we don't have another point to pin it down to tell you its exact direction. So on this graph, if I was trying to find the instantaneous rate of change at that point right there, I could draw the line like this, but like I could also draw the line like this, Or like I could draw the line like this, because those are all tangent at that particular point. We have no idea what direction it's actually going because we only have one point. And at one point, your line can tilt, still touching one point, all a bunch of different directions. So we had a problem. And to solve this problem is when we started developing calculus. So we're not going to actually do very many instantaneous rates of changes because that's the whole point of calculus. The beginnings of calculus, at least, is to figure out that question. But we'll approximate it today, so we'll get there. So here we go. Example 1. A rock is thrown off of a 50-story building. The distance the ball has fallen can be modeled by d of t equal to negative 16t squared plus 15t plus 500 feet in the first t seconds. So things to recognize, if you're in physics, the number negative 16 is gravity in feet. It's negative 9.81 in meters, but in feet it's approximated to negative 16, so this makes sense in real life. And notice again that our function does not have x's and y's. We're going to be using variables that make sense. T stands for time, D stands for distance. Great. We love when math makes sense. So what's happening here? So we have this building. Here's my building. And somebody threw a rock from the top. And when you know things about gravity, you know when you throw a rock, what is it going to do? Fall. Okay, great. So this is now the shape of my graph. We want to figure out a bunch of different things about this rock falling off of this building. The first thing we want to figure out is the average speed during the first 2 seconds of fall. So we have our idea here, and the ball or the rock is falling. So we want to know how much it has changed from time 0 to time 2, the average speed. So we're really trying to find this secant line's slope. And since we're finding a slope, we use the slope formula, which is the average rate of change formula. To use that, we need 2 output values. We need to know what's happening to the function at time 0 and what's happening to the function or the rock at time 2, which means all we have to do is plug in those values. This would be negative 16 times 0 squared plus 4.5 times 0 plus 500. This one's a slam dunk. The first 2 terms are 0, so it's at 500 feet. That makes sense. We haven't thrown the rock yet at time 0. At time 2, again, you're just going to be plugging in 2 to the formula itself to find the distance that it has traveled at time 2. So what did we get when we found how far the rock has fallen, its distance at time 2? Did y'all get 445? Fabulous. So we know at time 0, it's up at 500 feet. That makes sense. We haven't thrown it yet. Then we throw the ball and we count to 2 and then the rock. And then we say, how high is it now? It's at 445. So we have 2 points on our graph, essentially, that we can find the average rate of change. The average rate of change, remember, is the absolute value of the second distance minus the first distance divided by the second time minus the first time. It's literally just a slope with an absolute value on there. The absolute value button, I never remember because it wasn't on calculators when I used calculators in high school. It's on the math screen. Can somebody, on number? Math number, option 1 says ABS, correct? Okay, great. So there's the absolute value buttons. That's just something you can plug in your calculator because there are no variables left. We're just computing the average rate of change. Math, go over to number, and it's option 1. It says ABS. So remember, we're finding a speed here. We have feet on top, and we have seconds on bottom. So we're finding something in feet per second. How fast is this rock falling from time 0 to time 2? We should get 27.5. So let's figure that out. Okay, so we found the average rate of change of this rock falling at time 0 to time 2. Again, not how fast it's falling at a specific time, but the average between those two. Y'all have got part B. What is the rock's average speed or average rate of change from time 2 to time 5? As a hint, you need to find out how far it's fallen at time 2. We already know and how far it's fallen, or what height it is at time 5. I'll give you a second to figure out what that average rate of change is. So we get at time 5, the rock is now at 122.5 feet, right? Which means that if we find the average rate of change between these two, we are literally just using this fancy slope formula and doing the absolute value of 122.5 minus 445 over 5 minus 2. So we should have gotten here 107.5 feet per second. Now, there's some things I want you to notice about this so we can start verifying that this makes sense. Compare the two slopes together. The slope from the first problem is 27.5. The slope from the second problem is 107.5. Which slope is steeper?
The first one.
Oof. The second one, yeah. Remember, steepness, if it's like a big number, it's super steep. And this makes sense because if we draw a quick picture here of this rock falling, we're now checking from time 2 to time 5. And if I draw my secant line there, isn't that steeper than the first little mini drawing I had? That should happen. So if you ever get one that's not and you're like, wait a second, it should be steeper because it's been falling for longer, so gravity's been acting on it longer. This is where the mathematicians of ancient times were like, yeah, but what's happening to the rock at 3 seconds? Exactly. This is how we figured stuff out in the world, is we asked a lot of questions. So in part C, it's asking what is happening at the rocks what words were I just trying to say? What is the rock speed at exactly 3 seconds? We'd be finding the instantaneous rate of change. Right now, we don't have the tools to do that. I haven't shown you the calculus that it takes to do instantaneous rate of change. So we're going to get as close as possible, which means we're going to start utilizing the idea of limits in this problem. When we did limits, like back when we did the horizontal and vertical asymptotes in like September, we talked about limits as we get very close to a number, what is happening. So what are some input values that would be very close to 3 seconds? Closer. Closer.
2.99999.
Yes. So what we're going to do is we're going to estimate the average rate of change at 2.999. That's right before 3, but we need 2 points. So what's something like minutely after 3? 3.00. How many zeros do you want? But I'm just going to do 2 and then 1. If we find the distance that the rock is falling at these 2 times, they're minutely close to 3, and they're going to estimate for me the instantaneous rate of change because I'm taking a minute step away on the left side and a minute step away on the right side to then be able to do the average rate of change. So we'll fast forward through this because I know you can type stuff in your calculator. If you find the distance at 2.999, the distance that rock has fallen is 369.591 feet. And at 3.001, it's 369.408 feet. Again, this makes sense. It's falling, so it should be getting lower as your time goes higher. If we estimate the instantaneous rate of change by finding the average rate of change between a minute step away both directions, we can find a good approximation of the IROC, which means we're going to do 369.408 minus 369.591, absolute value, over 3.001 minus 2.999. We're as close to 3 as possible without actually using the number 3 so that we have an average between those, which would be 3. So if you calculate this, beep, 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 you can type it in your calculator. I know you can type things in your calculator. You'd get 91.5 feet per second. So this is our estimation of the instantaneous rate of change at time 3. It is not always going to work out perfectly that this is correct, but actually when you learn the calculus for this, This is going to make no sense to you yet, but d prime of 3, which is exactly what it's asking for when we learn what that means, would be negative 32 times 3 plus 45, which is actually 91.5 feet per second. So later on in your notes, when you find out what all that means, you'll look back at this and be like, oh, we were actually doing a good estimation of this, because it actually works out when you learn about the derivative of it and plugging in the value. So this is a good estimation. Not all the times are they that good and that accurate. This one just happens to be that good and that accurate. So if we're imagining ourselves to be those old mathematicians, like this is like BC's time. We're talking like way long time ago that this was all developed. We are trying to find the average rate of change of things. We start estimating the instantaneous rates of change, and we realize we need a way to talk about as things get really close to different values, which is where we started to work with limits. So we're going to do a quick introduction to limits. We'll spend a few days on limits themselves because they get more complicated than this, but this is the intro. Limits give us a language for describing how the outputs of a function behave as the inputs approach some particular value. In words, the definition of a limit is: if f of x becomes arbitrarily close to a single number L as x approaches c from both sides, then the limit of f of x as x approaches c is L. Ooh. It's saying that if the outputs get really close to some number as the inputs get close to some number. Those numbers don't have to be the same. And if that's the truth on both sides of the x value, then the limit of the function itself at that x value, or the c value, is the output L. Analytically, what that means in a math sentence instead of an English sentence is the following. The limit as x approaches c, do we remember how we're pronouncing these? The limit as x approaches c of f of x is L. This symbol right here stands for if and only if. If and only if. That's not a typo. There's two F's on purpose. If with two F's is if and only if. The right side limit is equal to the left side limit, which means we are going to be looking at the right side of numbers and at the left side of particular numbers to see what's happening on the graph, to see where the outputs are going towards. And if they're going towards the same number, then the limit is that number. So on a table, what that looks like. We want to know the limit as x approaches 7. So we look on the left side of 7. Notice that these numbers, aren't they getting very, very close to 7? If we, 6.99 and then 6.999, isn't that getting very, very close to 7? And if we look on the right side of it, aren't those numbers, if we look backwards, getting also very, very close to 7? So we're looking as the x values get close to 7 on both sides. So we look at the outputs here. What are the outputs, both sides, getting very, very close to? We have 2.598, 2.599. What is it getting close to? And on the other side, if we look inwards, we have 2.598, 2.599. What is it also getting close to? So since those numbers on both sides are getting close to 2.6, we can say that the limit is 2.6. Limits mean as we're getting very, very close on both sides. What is the output? It makes more sense to me to look at this graphically than in a table, so I'm hoping this next section kind of clears it up for you. We have 4 questions per input, and we have this crazy piecewise function. Remember, piecewise functions were the ones that like Frankensteined together and had like different parts. Yeah, this one has like a linear, couple quadratic sections, another linear, conic, whatever. So we have a couple questions here. This first question in each category says f of -4. That is asking what is the value of the function at -4, not the limit, but straight up, where is the closed dot? So at -4, what is the output value where the closed dot is? So here's -4 on the x-axis. Here's the function at -4. What is this output? -4. So f of -4 is -4. The next question says, what is the limit as x approaches -4? The answer is not -4. The answer is that we have to actually look at the left side and at the right side of -4 to see what the function is doing. So if we look at the left side of -4, that means we're looking just on this side of -4. Where is this graph going? What value? What is it getting close to? -2, but yeah. -2. And then if we look on the right side, so again, we're looking at -4, but on the right side, what is this value? What is it getting closer to as we get closer to -4? -4. Now, the reason I'm asking these questions is because we cannot answer the limit to the regular number unless the plus and the minus match. Do this plus and minus for the limits match? No, so we answer DNE, which stands for the limit does not exist. The limit does not exist, mean girls, okay? This is real things. It's an actual math thing. So again, we were looking at the x value of -4 for that problem. For the next problem, what's the x value that we're looking at? 0. Okay, f of 0 means I want to know exactly what is happening at 0 in the function. Maybe not necessarily the limits, actually definitely not necessarily the limits. But where is the closed dot at 0? 1. Okay, then we go to the limit. But to answer the regular limit, we have to look at the left side and the right side. Bless you. On the left side of 0, where is the function? -2. On the right side of the function, where is the limit? Sorry, on the right side of 0, where is the limit? 3. So did those match? No. So how do we answer the limit as x approaches 0? DNE does not exist. I got 3. It's a great question. So I'm looking at 0, and I'm going to look on the plus side. Here's the function on the plus side. What is it getting close to right there? 3.
So why wouldn't we use that?
What do you mean? Right here? Here.
Talk about the row 2.
This one? Because we're looking at 0.
But it's to the right of 0.
Yeah, but you're looking just minutely close to 0. So like, normally, if you're looking at 0, you look here. On the right side of it, you're not going to the right. You're looking on the right side of 0, which means this is the right side of 0, and I'm scooting in towards 0.
Like on the line of 0, but like this up to the right.
Correct.
Okay.
Yeah. Okay, let's do one more. Well, we have 3 more, but you know what I mean. We're going to be looking at the x value of 3. Here's the x value of 3. What is the value of the function at 3? Yeah, -1. It's not a weird spot here, which is interesting. Okay, we need to do the limits, which means we need to look on the left side and the right side. So if we look on the left side of 3, what is that value getting close to as we get closer to 3? What is the output like as we creep in closer to 3? -1. How about the right side? As we creep in closer to 3 from the right side, what is it also getting close to? -1. So we're looking at the x value of 3, but looking at the output as it gets close to it. The output is still -1. That's what the function is going towards. You're like squeezing it in to it on the left side and the right side. So since those values match, what is the limit as x approaches 3 regular? the same answer. They have to match for the limit itself to be the same number. Okay, now what about 5? What is the value of the function at 5? AKA, where's the closed circle? -2. Great, we want to do the limit, but we need to look on the left side and the right side of this before we can look at the limit. On the left side of 5, what is the function getting close to? -3. On the right side, what is the function getting close to? -3 again, which means since those match, what's the limit? -3. Now here's something interesting. Do you see a difference between the blue question and the green question?
Yeah,
So does the function's evaluation have anything to do with the limit? No. So don't get that confused. A lot of students get that confused. The evaluation at that point is not the same as the limit. The limit just has to match from side to side. Okay, then we go to number 8. 8 is interesting for a particular reason. Just looking at the graph itself, what's happening at 8? It's like it stops, and there's nothing on the other side of 8, right? So something interesting will happen. We can do f of 8. F of 8 is 0 because the function itself is being evaluated at 0. And to answer the limit question, I still look on the left and the right. What's it getting close to on the left? 0. What's happening on the right? What? Y'all see stuff on the right? We have no idea. So we can't even say does not exist. The actual way you would answer this one when it's on the edge of a graph and doesn't keep going is not enough info. Because we cannot see the left and the right, we can't answer the limit question. We don't know. We could answer left, but we couldn't answer right because there's nothing on the right side. So we have no idea what the limit is because the definition of a limit requires both sides to be equal. So it's not even does not exist. It's just like, you're like, I don't know. Not enough info. So the main goal of today, the front page of this was an introduction of why for calculus. This page is an introduction of what I want us to learn about, which is limits.